Communication Software Lab. Today, we'll do the experiment to simulate generation of double sideband suppressed carrier waveform for a single sinusoidal modulating frequency. We will repeat this for two different modulating frequencies and we're having an appropriate carrier signal. This is the frequency band diagram of the double sideband suppressed carrier. Dotted line shows that the carrier has been suppressed or removed, and we're left over with the upper sideband and the lower sidebands. The upper sideband denotes the FC plus FM, and the lower sideband denotes the FC minus FM as the extreme frequencies. The double sideband suppressed carrier is produced by using a balance modulator. The balance modulator is based on the nonlinear principles of the components like diode or the FET transistors. Here, the message signal and the carrier both, after passing through the balance modulator, produces the two bands, the upper sideband and the lower sidebands. So the output can be said as product of the modulating signal and the carrier signal. So if we use this relationship in the MATLAB with the coding, we can write that output is equal to MT dot into the carrier frequency, carrier signal. Let's go to the Octave and start the coding. T starts from 0 with an interval of 0.001 up to 1 second. This is the range of the graph that we're going to plot. AM is my peak amplitude of the modulating wave, and let's take it as 0.5. And FM modulating frequency taken as 5. The peak amplitude of the carrier is taken as 1. And the carrier frequency is taken as 10 times. So if it is 5, I'll take it as 50. Now, let's introduce the instantaneous value of the modulating signal. It is equal to AM sine omega mt. So it is taken as Vm is equal to AM sine omega is 2 pi FM. This is the modulating instantaneous value of the modulating wave. Similarly, the instantaneous value of the carrier signal is given by AC, and we are taking here AC cos omega ct. AC is given to us, AC. Cos, this is taken 90 degree out of phase with the sine, that is modulating. So cos 2 pi FC 2 pi FC t AC cos 2 pi FC t. Since into the balanced modulator, both of them are out of phase when they're fed. So VC is equal to AC cos 2 pi FCT. I've given two instantaneous values of VM and VC. Now my output. Suppressed carrier wave is given as the instantaneous value of the modulating signal is product of instantaneous product with the instantaneous value of the carrier. Now I like to plot these three waves. So I'll use subplot on 311, third row, first column, and first graph. Subplot, and I'll use plot. The graph is between the time and the voltage, instantaneous voltage. The title, modulating signal. And can give grid on. If it's optional if you want the grids. Grid on. And X label. I like to have time here, and X label, Y label, amplitude, and similarly subplot 312. This is for the second graph, and similarly the plot is between time and the instantaneous carrier voltage. and title has to be given carrier signal. Right on. And title with carrier signal. Carrier signal. Well, the same X label and Y label for the amplitude. And I'm straight away go for subplot for the third graph. So 3, 1, 3 plot. It's between time and the suppressed carrier, and the title morning just here plot. My P, the keyboard P is plot T comma plot T comma suppressed carrier, and it's between the title. I should write here title is double sideband suppressed carrier, double sideband suppressed carrier. So all the graphs are in one slide, and the upper one is about modulating, next is the carrier, and the third one is my double sideband suppressed carrier. We can just look at the point where the modulating signal crosses the zero amplitude. When it crosses the zero amplitude, we see the double sideband suppressed carrier inverts in phase. So this shows that this is a double sideband suppressed carrier. This is the output. We are done with this experiment.